Section 8.2 is going to be fitting lines to our data. So we're going to have scatter plots and we're going to find lines of best fit. And a line of best fit is just a line that fits the data, our scatter plot, the best, with trying to have the same amount of dots above and below it. And this line of best fit can go through dots on the scatter plot. But we want to try to have it in the middle to show the best representation of the scatter plot. So for our first example here, the table lists the median age of females living in the U.S. based on the results of the U.S. Census over the past few decades. Determine whether a linear model is reasonable for the data. If so, find a linear model for this data. So in this chart here, we are given the year and the median age of the females. And over here, we are going to simplify our calculations by letting X represent the time in years after 1970. So looking right here, our first year is 1970, so that is 0 years from 1970. 1980 would be 10 years. 1990 would be 20 years. 2000 is 30 years. And 2010 would be 40 years. And now we're going to use this information here to draw a scatter plot. So I'm going to do my best because I'm hand drawing here. So our x-axis is our years. So we have 10, 20, 30, and 40. And then for our y-axis, we are going from 29 to 38.2. So I'm going to make a little squiggly here saying we're not starting at 0, and I'm going to go up by 1s. All right, so we're going to plot our information. 0 is 29.2, so it's going to be just above the 29. 10 is 31.3. 20 is exactly 34. 30 is 36.5. And 40 is 38.2. And now we're going to try to draw a graph here. Now, I'm going to try to do my best here without using a ruler. So instead of wasting time on the video, I just kept doing it until I got a good one here. As you can see, we have this dot down here is underneath. We have one above. It's going through this one. This one is underneath, and it's going through this one. So we have 2 underneath, 1 above, and it's going through 2. So that's pretty close. So for our next step, we have to find the equation for this line. So because this line is going through these 2 points right here, this point and this point, we're going to use those 2. So the first one is 20 and 34, and the other one is 40, 38.2. We're going to use those 2 points to find the slope. So step 1 is to find slope. And we have to use y2 minus y1 over x2 minus x1. So 38.2 minus 34 over 40 minus 20. And that would equal 4.2 over 20, which would simplify down to 21/100ths. Then for step 2, we have to find the y-intercept. And we do that by plugging in what we know in the linear equation model, y equals mx plus b. So we just found the slope, and that was 0.21. So that's our m value. And we have two ordered pairs up here that we just used that we know are on the line. And I'm going to pick the 20, 34 because they're both whole numbers. So our y is 34. And our x is 20. And we're going to use that to solve for b now. So if I do 0.21 times 20, I'm going to get 4.2 plus b, and that would give us 34. So then I solve for b, so I minus 4.2 from both sides, and I get 29.8 equals b. So now I have a slope and I have a y-intercept. So I can write the equation y equals 0.21x plus 29.8. So that would be the equation for the line that I drew above. Now we're going to move on here, and we're going to talk about a residual. And a residual is the signed vertical distance between a data point and a line of fit. So here, this is a good picture here to show you. So we have the line of best fit going through these points. And these are the points. And the dotted lines represent the distance that those points are away from that line of best fit. And that distance is the residual. So some of them are going to be negative and some are going to be positive. And then over here we have the residual plot. And if they are all close, once we graph our residual numbers, if they're all close to the x-axis, so pretty close to it, then that fits the data very well. And here in the middle, if they're all over away from the x-axis, it's a weak model. And then if for the third one here, if the dots are all over the place, then it's not fitting the data very well. And also you can look and see that on that third graph, it's not really random. It's kind of in a V-shaped pattern for the dots. And also there's 4 above the x-axis and only 2 underneath, so it's not really distributed evenly as well. So that does not fit very good. All right, so for this example, we're going to consider the data from the previous example, only this time they're telling us that the line of best fit is 0.25x plus 29. So it's pretty close to the one we just found. It's a little bit different. And the same thing, x is the year since 1970 and y is the median age. So in this chart, they gave us the x's that we used. They gave us the y values that we used. But now we got to use their line of best fit, their equation here, to figure out what the points would be for that equation. So we're going to have to plug in 0 for x. So we're going to have 0.25 times 0 and then add 29. So that one's going to be 29. And then we're going to plug 10 in there instead of the 0. And we would get 31.5. Then we're going to plug 20 in and we would get 34. Then we'd plug 30 in and we'd get 36.5. And we'd plug 40 in and we'll get 39. Okay, so now is where we find the residual. And it's actually quite simple. We subtract the predicted amount from the actual. So we take the actual minus the predicted. So actual minus predicted. You probably want to write that down. So we want 29.2 minus 29. So that would give us 0.2. 31.3 minus 31.5. We're going to do, that would be negative 0.2. 34 minus 34 is 0, and 36.5 minus 36.5 is also 0. And then we have 38.2 minus 39, and that would give us negative 0.8. So those are our residuals. Those are how far away from our line that those actual dots are. And then we are going to plot these residuals. So I'm going to erase this so it's out of my way here. And I am going to, this is my x-axis. So remember we have 10, 20, 30, and 40. And then our residuals go from -8 up to 0.2, or -0.8 up to 0.2. So I think I'm going to go by 0.4s. That would be -0.4 and -0.8. And our 0, we got 0.2 right here. So 0 is 0.2, would be right there. 10 is -0.2. So 10 is going to be about right there. And 20 is 0. 30 is 0 as well. And 40 is -0.8. So now looking at this, they're all pretty close to the x-axis, if not on the x-axis. So because they're all pretty close, this is a good fit. We can tell that that equation is a good fit. Now, not everybody's equation is going to be the exact same, because when you draw your line, you may draw it just a tad bit different, just like we got a different equation when we did this problem before. All right, interpolation and extrapolation. So interpolation is making a prediction based on a value within the model's domain, and extrapolation is based on a prediction on a values outside of the domain. So what that means is if we are plugging in numbers, like for instance, in our example, we use the numbers for x 0 to 40. So if we plug in a number that's between that, it's going to be an interpolation. If it's a number outside of 0 to 40, it's an extrapolation. So suppose you use the data from the table in the Explore activity to derive the model y equals 0.25x plus 29, where x is the number of years since 1970, and y is the median age of the females in the US. Use this model to predict the median age of females for the years 1995 and 2015. State whether each prediction is an interpolation or an extrapolation. So we're using all of that information from before, but now we have different years to plug in. So our first equation, our x value, 1995 is 25 years away from 1970, so we have to plug in 25 for x. And when I plug this in, 0.25 times 25 plus 29, we get 35.3. So the average age, or the median age in 1995 is 35.3. And because we plugged in 25 for the x, and remember our x values were between 0 and 40 in those charts we used, so this would be an interpolation because it's in between those numbers. And then for this one, we're going to use the same equation, but we're going to figure out for 2015. And 2015 is 40 years, or 45 years away from 1970. So we're going to have 0.25 times 45 plus 29. And when I do that math, I get 40.3. And because we plugged in the number 45 and it's outside of the numbers 0 through 40 that we used for x, this is an extrapolation.